Mauritius, and welcome to this section of grade 10 CBSE physics class. Today we are looking at the chapter number 1, light, reflection and refraction. In this chapter, we are going to study in detail about the phenomenons reflection and refraction. So we are having major two topics in this chapter. One is reflection and other is refraction. We need to study the whole details related to reflection and refraction. So our first topic, I am splitting this chapter into two sections, reflection and refraction. First we start with the reflection, then study all the topics related to the reflection, then finishes the reflection, and after finishing reflection, we will go through refraction. The same procedure, again we will study all the topics related to refraction and then we finishes the refraction. So starting with the reflection. What do you mean by a reflection of light? What do you mean by a reflection of light? Suppose when we are considering a light ray, when we are considering a ray of light and the ray of light incidents on a smooth surface and the ray of light incidents on a smooth surface. When this ray of light incidents on a smooth surface, it bounces back. This phenomenon is known as a reflection of light. This phenomenon is known as a reflection of light. When a ray of light incidents on a smooth surface, it reflects back or it bounces back. This phenomenon is known as a reflection of light. So we can define reflection as it is the phenomenon of light in which when a ray of light incidents on a smooth surface and it bounces back. So the ray of light which incidents on the surface, is known as the incident ray. And the ray of light which bounces back from the smooth surface, is known as the reflected ray. And when we are considering a perpendicular to the surface, then this perpendicular is known as normal. Now look at this figure. This is the schematic representation of a reflection of light. When a ray of light incidents on a smooth surface, it bounces back. And this phenomenon of light is known as reflection. The ray of light which incidents on the surface is known as the incident ray. The ray of light which bounces back from the surface is known as the reflected ray. The perpendicular drawn to the surface is the normal. Now look here. There is an angle between the incident ray and the normal. This angle is known as angle of incidence. There is an angle between the incident ray and the normal. This angle is known as angle of incidence. There is an angle between the reflected ray and the normal. This angle is known as angle of reflection. So what is angle of incidence? Angle of incidence is the angle between incident ray and the normal. It is represented by small letter I. What is angle of reflection? Angle of reflection is the angle between a reflected ray and the normal. And it is represented by the small letter r. So what are the terms related to reflection? Incident ray, reflected ray, normal, angle of incidence I, angle of reflection r. So what do you mean by basically what is reflection? When a ray of light incidents on a smooth surface and if it bounces back, then the phenomenon is known as a reflection. The ray which incidents on the surface is the incident ray. The ray bounces back from the surface is the reflected ray. The perpendicular drawn to the surface is the normal. The angle between incident ray and the normal is the angle of incidence. The angle between reflected ray and the normal is the angle of reflection. Angle of incidence is represented by small letter I and angle of reflection is represented by small letter r. This is what called a reflection of light. Now moving to laws of reflection. We need to study laws of reflection. What are the laws related to reflection? So that is laws of reflection. We have two laws to study related to reflection. The first one is the incident ray, a reflected ray and the normal lies on the same plane. The incident ray, a reflected ray and the normal at the point of incidence lies on the same plane. Incident ray, reflected ray and the normal at the point of incidence lies on the same plane. This is the first law. Second one is angle of incidence is equal to angle of reflection. That is I is equal to R. That is I is equal to R. So what are the laws of reflection? First one is incident ray, reflected ray and the normal to the surface at the point of incidence lies on the same plane. Incident ray, reflected ray and the normal to the surface at the point of incidence lies on the same plane. This is the first law of reflection. And the second law of reflection is angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. That is I is equal to R. These are the two laws of reflection. So we discussed about what is reflection and the two laws of reflection. Now we need to discuss about spherical mirrors. Now we need to discuss about spherical mirrors. Mirrors are those surfaces. Mirrors are those surfaces which produces image due to reflection. Mirrors are those smooth surfaces which produces image due to reflection. And if the reflecting surface is a spherical surface, if the reflecting surface is a spherical surface, then such mirrors are called as spherical mirrors. So here we are studying two types of spherical mirrors, which are concave mirror and convex mirror. Here we are studying two types of spherical mirrors, concave mirror and convex mirror. Here we are studying two types of spherical mirrors, concave mirror and convex mirror. Concave mirror means the mirror in which a reflecting surface curved inwards. Concave mirror means the mirror in which a reflecting surface curved inwards. A reflecting surface curved inwards. If the reflecting surface curved inwards, then such mirrors are known as concave mirror and can be drawn like this. And the non-reflecting surface is represented by these drawing lines. And the non-reflecting surface is represented by these drawing lines. So this is the reflecting surface and the reflecting surface is curved inwards. Such type of mirrors are known as concave mirror. So next is convex mirror. In case of convex mirror, the reflecting surface curved outwards. If the reflecting surface of mirror, curved outwards, then such type of mirrors are known as convex mirror. And can be drawn like this. Look here, The non-reflecting surface is represented by drawing such lines, and this is the reflecting surface and is curved outwards. Such mirrors are known as convex mirror. Such mirrors are known as convex mirror. So a mirror is simply a smooth surface which produces image due to reflection, and the reflecting surface is a spherical surface, then it can be called as a spherical mirror. We are studying two types of spherical mirror. Mainly we are studying two types of a spherical mirror, concave mirror and convex mirror. Concave mirror means the reflecting surface curved inwards. If the reflecting surface curved inwards, then such type of mirrors are known as concave mirrors, can be drawn like this. And if the reflecting surface curved outwards, then such type of mirrors are known as convex mirror, and we can draw convex mirror like this. Now we need to study some terms related to mirrors. Now we need to study some terms related to mirrors. We need to study some terms related to mirrors. So for studying the term, I am drawing the figure of a mirror. Here I am taking concave mirror. Here I am taking concave mirror. And now I am marking the point P. Look, this point P is the center of the reflecting surface. This point P is the center of the reflecting surface and is known as pole. So the first term related to mirror is pole. What do you mean by pole? The center of the reflecting surface is the pole. Center of the reflecting surface is the pole, represented by the letter P. Now I am drawing a straight line axis which is passing through this pole. Now I am drawing a straight line axis which is passing through this pole. This straight line axis passing through the pole is known as principal axis. This straight line axis passing through the pole is known as principal axis. So what do you mean by principal axis? The straight line axis passing through the pole is known as the principal axis. Now I am marking a point denoted by capital letter F, and this point is known as focus. This point is known as focus. What do you mean by focus of a mirror? The reflected rays from the mirror meet at a point called focus of the mirror. The reflecting rays from the mirror meet at a point called focus of the mirror. So when light rays reflected from this mirror meet at a common point, and this common point is marked as F, and this point is the focus of the mirror. This point is the focus of the mirror. The next point I am marking is C. C means center of curvature. C means center of curvature. C means center of curvature. What do you mean by center of curvature of a mirror? Now, when I extend this mirror, we got a spherical surface. When I extend this mirror, we got a complete spherical surface. The center of this spherical surface is the center of curvature. So this mirror is the part of that spherical surface. When I complete this, we got a whole sphere, and this mirror is a part of that sphere. So what is the center of that sphere? Then the center of that sphere is known as center of curvature. So we can say that the center of the sphere in which mirror is a part is the center of curvature. The center of the sphere in which the mirror is a part is the center of curvature. Next term I am going to define is radius of curvature. Radius of curvature. So you all know that radius of the sphere is the distance between the center and the surface of the sphere. So C is the center of curvature. and the distance between the center of curvature and the pole. Pole is the point on the surface of the sphere, on the surface of the spherical mirror. So this distance is the radius of curvature. Simply we can say that radius of the sphere in which the mirror is a part. Radius of curvature is the radius of the sphere in which the mirror is a part. So pole, principal axis, focus, center of curvature, radius of curvature. Now we have a relation between. Now one more term we need to define. What is focal length? Next term, what is focal length? Focus is denoted by capital letter F and focal length is denoted by small letter f. Focus is denoted by capital letter F and focal length is denoted by small letter f. Focal length is the distance between focus and the pole. Distance between focus and the pole is the focal length. Now we need to define a relation between the focal length and the radius of curvature. From this figure, it is clear that twice the focal length gives the radius of curvature. That means we can say that radius of curvature r is equal to 2 into focal length. This is the relation between radius of curvature and focal length. So we can say that r is equal to 2f. So radius of curvature is equal to 2 into focal length. That means double the focal length gives radius of curvature. Double the focal length gives radius of curvature. So what are the terms we explained right now related to the mirror? First one is pole. What do you mean by pole? The center of the reflecting surface is the pole. Second is principal axis. What is principal axis? The straight line axis passing through the pole is the principal axis. Next is focus. What is focus? The reflected rays from the mirror meet at a common point known as focus of the mirror, represented by capital letter F. Then what is center of curvature? The center of the sphere in which the mirror is a part, represented by letter C. Then what is radius of curvature? Radius of the sphere in which the mirror is a part, represented by the letter R. Then focal length. It is the distance between focus and pole. It is the distance between focus and pole, represented by small letter f. Then what is the relation between radius of curvature and focal length? Radius of curvature is double the focal length. Radius of curvature is double the focal length. So we can say that r is equal to f by 2f. R is equal to 2f. Otherwise, we can say that f is equal to r by 2. Otherwise, we can say that f is equal to r by 2. Either r is equal to 2f, otherwise f is equal to r by 2. That's the relation between radius of curvature and focal length. These are the terms related to spherical mirrors. Next, we need to study the image formation by the spherical mirrors. Very, very important topic, image formation by spherical mirror. So, we are going to study the image formation. Image formation by spherical mirrors. Image formation by spherical mirrors. So for studying image formation, we need to study some basic laws. We are having 3 basic laws. Using these 3 basic laws, we can draw all the image formation figures. So the first law is that when a ray of light coming parallel to the principal axis, when a ray of light coming parallel to the principal axis, after reflection passes through the focus. So if a ray of light is coming parallel to the principal axis, then after reflection from the mirror, it must passes through the focus. It must passes through the focus. Now we can draw the figure. This is a concave type mirror. Pole, focus, center of curvature. So when a ray of light coming parallel to the principal axis, this is the ray of light coming parallel to the principal axis. This ray of light, after reflection from the mirror, passes through the focus. So this must pass through like this. The ray of light should pass through like this. This is parallel to the principal axis. After reflection from the mirror, passes through the focus. Now we can consider the case of a convex mirror. I am considering the case of a convex mirror. Pole, focus, center of curvature. So when a ray of light passing parallel to the principal axis, after reflection goes like this. When this ray of light is extended to the other side, then it will pass through the focus on the other side. That means focus behind the mirror. And the ray of light passes, focus behind the mirror. Okay. Now, this is the first law. When a ray of light coming parallel to the principal axis, after reflection from the mirror, passes through the focus. This is the case for both concave and convex. Now the second case is when a ray of light coming through the focus, after reflection from the mirror, passes parallel to the principal axis. Now we can draw the case. First, this is a concave mirror. This is the principal axis, pole, focus, center of curvature. When a ray of light coming through focus, then after reflection from the mirror, it passes parallel to the principal axis. So look here, the ray of light is coming through the focus. After reflection from the mirror, it passes parallel to the principal axis. Okay. Now we consider the case of a convex mirror. This is the convex mirror. Pole, focus, center of curvature. This is the focus. This is the focus behind the mirror. Now a ray of light coming through focus. This is the ray of light coming through focus. After reflection from the mirror, passes parallel to the principal axis. Ray of light coming through focus. After reflection from the mirror, passes parallel to the principal axis. This is the second case. Now moving to the third case. In the third case, it says that when a ray of light passing through center of curvature will retraces the same path. That means it never changes the path. When the ray of light is coming through center of curvature, then after reflection from the mirror, it retraces the same path. So this is the case of concave mirror, pole, focus, center of curvature. When a ray of light coming through center of curvature, after reflecting from the mirror, retraces the same path. The case is same for convex mirror. Pole, focus, center of curvature. When a ray of light coming through center of curvature, after reflection from the mirror, retraces the same path. So these are the three cases, or we can say these are the three laws which we need for drawing image formation, plotting image formation or drawing image formation by concave or convex mirror. So which are the three cases? First one, when a ray of light coming parallel to the principal axis, after reflection passes through the focus. After reflection passes through the focus. Second case, when a ray of light coming through focus after reflection passes parallel to the principal axis. After reflection passes parallel to the principal axis. Now the third case, which is the third case, when a ray of light coming through center of curvature after reflection retraces the same path. After reflection retraces the same path. So using these three laws, we need to draw the image formation by concave mirror and image formation by convex mirror. So first we can start with the cases of concave mirror. So we can start with the case of concave mirror. Now I am going to start with concave mirror. So in concave mirror, we need to study 6 cases of image formation. In concave mirror, we need to study 6 cases of image formation. So we can draw the 6 cases of image formation in concave mirror. In concave mirror, we need to study 6 cases. So first starting with the concave mirror. We need to study 6 cases. First case, when the object is placed at infinity or when the object is at infinity. First case, when the object is at infinity. Object is at infinity, where the image have been formed, where the image is formed. So we need to draw the case and find where the image is formed and the size of the image and the nature of the image. So I am drawing a concave mirror. This is the concave mirror. I am drawing the principal axis, marking pole, focus, center of curvature. Pole, focus, center of curvature. Where is the object? Object is at infinity. Object is at infinity. So we cannot draw the object. Only the rays coming from the object can be drawn like this, which is parallel to the principal axis. Only the rays coming from the object can be drawn like this, which is parallel to the principal axis. Now recollect what we studied in the law for image formation. In the first law, it says that when a ray of light coming parallel to the principal axis after reflection passes through the focus. So these rays must passes through focus after reflection. So after reflection, this one passing through focus and this one also passing through focus. So these reflected rays together meet at the point focus. So these reflected rays together meet at the point focus. So we can say that image is formed at focus. So we can say that image is formed at focus. Image at focus. So what is the first case? If the object is at infinity, then the image is formed at focus. Then what is the size of the image? What is the size of the image? You know that, look here. This is highly diminished or point sized. The size of the image is very, very small. So we can say that size of the image is highly diminished or point sized. Highly diminished or point sized. Highly diminished or point sized. Then what is the nature of the image? The nature of the image is real and inverted. The nature of the image is real and inverted. So this is the first case of image formation in concave mirror. First one, when the object is at infinity, then the image is at focus. This is the figure. Size of the image is highly diminished or point sized. Then nature, real and inverted. Nature of the image is real and inverted. This is the first case. Now we can go through the second case. In the second case, I am interchanging the positions. So the object is placed at focus. So the object is placed at focus. We need to find where the image is formed. We need to find where the image is formed. Now we can draw. I am taking the same picture. Center of curvature, focus and pole. Object is placed at focus. So I am placing the object at focus. This is our object. I am calling it as OB. I am calling it as OB. So a ray of light first coming parallel to the principal axis. A ray of light coming parallel to the principal axis. You all know that the ray of light coming parallel to the principal axis after reflection should pass through the focus. After reflection should pass through the focus. Okay. Second one, I am taking the ray of light coming through the center of curvature. You all know that a ray of light coming through center of curvature after reflection will retrace us the same path. So look here, these rays are not meeting. These rays are not meeting. We hope that this will meet at anywhere in infinity. We hope that they will meet at anywhere in infinity. So we are taking image is formed at infinity. So we are taking that image is formed at infinity. When it is meeting at infinity, then the size of the image is highly enlarged. Then the size of the image is highly enlarged. Then what is the nature of the image? Nature of the image is real and inverted. Nature of the image is real and inverted. So this is the second case. This is the second case. What is the second case? When the object is at focus, image is at infinity. You can study easily like this. First case is object at infinity and image at focus. Just reverse the condition. Object at focus and image at infinity. When the object is at focus, image should be formed at infinity. And the size of the image is highly enlarged. Nature of the image is real and inverted. This is the second case. We have 6 cases in concave mirror and 2 cases in convex mirror. So we need to study the 8 cases. This is the second one. Moving to the third case. Moving to the third case. Now moving to the third case. Taking the same figure of mirror. Pole, focus, center of curvature. Okay. Then the third case is object beyond C. Object beyond C. We are placing object just the back of C, just beyond C. We are placing the object just behind C. So I am placing the object here. This is our object. Now we need to complete the figure and find where the image is formed. So ray of light first coming parallel to the principal axis after reflection from the mirror passes through the focus. Okay. Second one, ray of light passing through center of curvature after reflection retraces the same path. Where these two rays meet, these two rays meeting at a point between C and F. Between C and F. So this is the image. These two rays meet at a point between C and F. So we can say that image between C and F. Image between C and F. Now look at the size. This is the size of object and this is the size of image. So we can say that size of the image is small. Otherwise we can say that the size is diminished. Otherwise we can say that the size is diminished. Then nature of the image is real and inverted. Nature of the image is real and inverted. So this is the third case. The third case is object beyond C. When we place the object beyond C, we get the image between C and F. We get the image between C and F. And the size of the image is diminished, small image. And the nature is real and inverted. This is the figure corresponding to the case. Okay. Now we can move through the fourth case. Now we can move to the fourth case. Fourth one. Already I said that first case, which is the object at infinity and image at focus. When we reverse the case, we got the second case. So same condition we can apply here. Just reverse the position of object and image, then we got the fourth case. So now I am placing the object between C and F. Now I am placing the object between C and F. Object between C and F. We need to find the position of image. Okay. So I am using the same image. Pole, focus, center of curvature. So this is the fourth case where the object is placed between C and F. So I am placing the object between C and F. This is our object. A ray of light passing through focus. A ray of light passing parallel to principal axis. After reflection passes through the focus. Now a ray of light passing through center of curvature. After reflection retraces the same path. Now where these rays meet together beyond C. These rays meet together beyond C. So where is the image formed? Image formed beyond C. Image formed beyond C. Now look at the figure. This is the size of object. This is the size of image. From this figure itself, it is clear that size of the image is enlarged. Size of the image is enlarged. Size of the image is enlarged. Then what is the nature of the image? Nature of the image is real and inverted. Nature of the image is real and inverted. Nature of the image is real and inverted. So the reverse of third case is the fourth one. Just reverses the position of object and image. That is object between C and F. Then image beyond C. Size is enlarged and the nature of image is real and inverted. This is the fourth case. So when first case is reversed, we got the second one. When the third case is reversed, we got the fourth one. Now we are moving to the fifth case. Now we are moving to the fifth case. Same image we can use for focus and the center of curvature. The fifth case is object at C. Now I am placing the object exactly at C. Now I am placing the object exactly at C. So this is the object. I am placing the object exactly at C. So a ray of light parallel to the principal axis after reflection passes through the focus. Okay. Now the object is exactly at C. So we cannot draw a ray of light passing through center of curvature. So we are using the second condition here. A ray of light passing through focus after reflection coming parallel to principal axis or passes parallel to principal axis. So this is the case. So first a ray of light parallel to principal axis after reflection from the mirror passing through focus. Next ray of light coming through focus after reflection from the mirror passes through Parallel, passing parallel to principal axis. Now look, these two rays meet at a point. These two rays meet at a point. Where is the point? Exactly at C itself. Exactly at C itself. So image is exactly at C. Now look at the figure. This is image. Now look at the figure. What is the size of object and size of image? Look at the size of object and size of image. They are exactly same size. They are of same size. So image is of same size. Image is of same size. Then what is the nature? Nature is real and inverted. Nature is real and inverted. Nature is real and inverted. Okay. So this is the fifth case. Object at C, image formed exactly at C itself. The size of the image is same size and the nature is real and inverted. Now we can move through the last case of concave mirror. Last case of concave mirror, which is the sixth case. Which is the sixth case. Now this is the last case of concave mirror. Then after this we are having two cases for convex mirror. After this, we are having two cases for convex mirror. In this figure also, I am using the same image. Focus, center of curvature. Now, I am placing the object between F and P. Now, I am placing the object between F and P. So, I am placing the object here. When a ray of light coming parallel to the principal axis, after reflection passes through the focus. Next one, ray of light. Next one, ray of light passing through center of curvature after reflection retraces the same path. When both these lines extended to the backwards, they meet at here. So here is the image formed. What is the peculiarity of this image? This image is formed behind the mirror. This image is formed behind the mirror. That's a very important peculiarity. This image is formed behind the mirror. Now look at the size of the image. It is enlarged. Image is enlarged. So when an image is formed behind the mirror, then the nature is virtual and direct. When an image is formed behind the mirror, then the nature is virtual and direct. When an image is formed behind the mirror, then the nature is virtual and direct. So this is the last case of image formation of concave mirror. Here the object is placed between F and P, that is focus and pole. Object is placed between focus and pole. Where is the image formed? Image formed behind the mirror. Image is formed behind the mirror. And the size of the image, it is an enlarged image. Whenever the image is formed behind the mirror, then the nature is virtual and direct. Then the nature is virtual and direct. That's all about the image formation of concave mirror. That's all about the image formation of concave mirror. Now we need to study image formation of convex mirror. So next is image formation of convex mirror. Image formation of convex mirror. Here in convex mirror, we are having only two cases. We need to study only two cases of image formation in convex mirror. So in total, for concave mirror, we are having 6 cases, and for convex mirror, 2 cases. So in total, 8 image formation for spherical mirror. So in total, 8 image formation for spherical mirror. So now image formation by convex mirror. The first case, I am placing the object at infinity. Object at infinity. We need to find where the image is formed. We need to find the size of the image. We need to find the nature of the image. Okay, we can draw. This is the convex type of mirror. So I am drawing a convex mirror. This is a convex mirror. Principal axis, pole, focus, center of curvature. This is the focus behind the mirror. So first case, so object at infinity. So we cannot draw the object, just we can draw the rays coming from the object. That is the rays coming from the object that is parallel to the principal axis. The rays coming from the object that is parallel to the principal axis. Just go like this. And by law, we know that the rays coming parallel to the principal axis after reflection passes through the focus. So when we extend these rays to the backward direction, they will pass through the focus. When we extend these to the backward direction, they will pass through the focus. So image is formed at focus. Image is formed at focus. But it is behind the mirror. Image is formed at focus, but it is behind the mirror. Now, what is the size of the image? Size of the image is highly diminished or point sized. Size of the image is highly diminished or point sized. And the nature is, whenever the image is behind the mirror, then the nature is virtual and erect. So this is the first case of image formation by convex mirror. Object at infinity, then the image is formed at focus but behind the mirror. And the size of the image is highly diminished or point sized, and the nature of the image is virtual and erect. This is the first case. Now we can study the second case, which is the last case of image formation by spherical mirror, which is the last case of image formation by spherical mirror. So I am using the same figure, just rubbing only the rays. Okay, focus. Okay. So in last case, we can place the object anywhere between. We can place the object anywhere between infinity and pole. Between infinity and pole. Between infinity and pole, anywhere we can place the object. So I am placing the object here. This is our object. First a ray of light coming parallel to the principal axis. After reflection, sorry, this is the case of a convex mirror. So after reflection, it passes through the focus. Okay. So next case, and the ray of light passing through center of curvature retraces the same path. Look, these two meet between pole and focus behind the mirror. These two meet between P and F. So we can say that image between P and F behind the mirror. Image between P and F behind the mirror. Now look at the size of the image. Size of the image is diminished. It is small image. Size of the image is diminished. It is small image. What is the nature? Whenever the image is formed behind the mirror, then the nature is virtual and erect. Then the nature is virtual and erect. This is the last case. What is the last case? When the object is placed between infinity and pole, then the image formed between pole and focus behind the mirror. Then what is the size of the image? Size of the image is diminished and the nature is virtual and erect. So now we complete all the 8 cases of image formation. 6 from concave mirror and 2 from convex mirror. Very, very important topics. You need to study. You must study all the 8 cases of image formation. Okay. Now we completed all the 8 cases of image formation. That means image formation is completed. Then we need to study the uses of concave mirror and the uses of convex mirror. So concave mirror uses and convex mirror uses. Concave mirror uses. This concave mirror is commonly used in torches. This concave mirror is commonly used in torches. That is the first use. It can be used in torches. The second one, concave type mirrors are used in searchlights. In searchlights, this type of mirrors are used. And the third one is used in headlights of vehicles. Used in headlights of vehicles. Used in headlights of vehicles. The fourth one, dentist use this mirror. Dentist use this mirror to get large image. To get large image of teeth. To get large image. Fifth one, this type of mirrors is used as shaving mirrors. This type of mirrors is used as shaving mirrors. And the last one, it is used in solar furnace. It is used in solar furnace for concentrating sunlight. It is used in solar furnace for concentrating sunlight. So what are the uses of concave mirror? It is used in torches. It can be used in searchlights, used in headlights of vehicles. Dentists use this mirror to get large image. Then this can be often used as shaving mirrors. This is used in solar furnace to concentrate sunlight. Then uses of convex mirror. Uses of convex mirror. Convex mirror. These mirrors are used as rear view mirror in vehicles. These mirrors are used as rear view mirror in vehicles. So these are the uses of concave and convex mirror. Concave mirror are used in torches, searchlights, headlights, and as shaving mirrors. Often this is used in solar furnace for concentrating sunlight. Dentists also use such type of mirror to get large image. Convex mirror is used as a rear view mirror in vehicles. Convex mirror is used as rear view mirror in vehicles. These are the uses of concave and convex mirror. Now we need to study the next topic, which is sign convention. What do you mean by sign convention? What are the things to be obeyed by sign convention? So next we are going to discuss about sign convention. So whenever we are considering image formation, this is the principal axis, pole, focus, center of curvature. The first point to be noted in sign convention is that object should be placed in the left side of the mirror. The first point to be noted that object should be placed in the left side of mirror. That means the ray of light coming from the object should be from the left hand side. The ray of light coming from the object should be from the left hand side. So first point to be noted is that object should be placed on the left side of the mirror. Second point is noted that all the measurements are taken from pole. So when we are considering a coordinate system, you know that all the measurements are taken from the origin. All the measurements are taken from the origin. Like the same way, similar to origin, here we are considering the measurements from pole. Here we are considering the measurements from pole. So towards the right of the pole, all measurements are taken as positive. Towards the right of the pole, all measurements are taken as positive. Towards the left of the pole, all measurements are taken as negative. Towards the left of the pole, all measurements are taken as negative. Then from downwards, all measurements are taken as negative, and in the upward direction, all measurements are taken as positive. In the upward direction, all measurements are taken as positive. So from sign convention, what all points we need to remember? First one, object should be placed at the left side of the mirror. That means rays coming from the object is from the left hand side. Next, all the measurements are taken from the pole. Towards the right of the pole, all measurements are taken as positive. Towards the left of the pole, all measurements are taken as negative. And in the upward direction, measurements are positive, and in the downward direction, measurements are negative. All are based on the position of pole. This is sign convention. This is sign convention. Next, we need to study the mirror formula. Next, we need to study the mirror formula. What is mirror formula? This is simply an equation. This is simply an equation. Mirror formula. This is mirror formula. What is mirror formula? 1 by V plus 1 by U is equal to 1 by F. 1 by V plus 1 by U is equal to 1 by F. Where what is V and U? The distance of the image from the pole is taken as V. The distance of the image from the pole is taken as V. The distance of the object from the pole is taken as U. The distance of the object from the pole is taken as U. And F is the focal length. F is the focal length. So what is the equation? 1 by V plus 1 by U is equal to 1 by F. 1 by V plus 1 by U is equal to 1 by F. 1 by V plus 1 by U is equal to 1 by F. This is mirror formula, where V is the distance of image from the pole, U is the distance of object from the pole, and F is the focal length. This is mirror formula. The next topic is magnification. Next topic is magnification, represented by small letter m. Represented by small letter m. Magnification is defined as the ratio of height of image to height of object. Magnification is defined as the ratio of height of image to height of object. So we can write m is equal to hi by ho, where hi is the height of image and ho is the height of object. Hi is the height of image and ho is the height of object. So we can write m is equal to hi by ho. Otherwise, we can write m is equal to minus v by u. Otherwise, we can write m is equal to minus v by u. So two equations for magnification. M is equal to hi by ho and m is equal to minus v by u. So what is magnification? Magnification is defined as the ratio of height of image to height of object. Magnification is defined as the ratio of height of image to height of object. That is m is equal to hi by ho. Otherwise, we can write m is equal to minus v by u. That's magnification. That's magnification. Okay, clear? So that's all about the first topic, reflection. That's all about the first topic, reflection. We completed the first section, reflection. What is reflection? Terms related to reflection, spherical mirrors, which is convex and concave type, image formation by convex and concave type, uses of convex mirror and concave mirror, sign convention, mirror formula, and magnification. That's all about the first topic, reflection. Okay. So we completed our first main section, reflection, and now we are moving to the next section, that is refraction. So basically, what do you mean by refraction? When a ray of light is traveling from one medium to another, when a ray of light is traveling from one medium to another, then the path of light bends. Then the path of light bends, and this phenomenon is known as refraction. So simply we can say that the phenomenon of bending of light when it travels from one medium to another, the phenomenon of bending of light when it travels from one medium to another is called a refraction of light, is called a refraction of light. So when we are considering two mediums, so when we are considering two mediums, this is glass, and the ray of light is coming from air. The ray of light is coming from air. So air is the first medium. So air is the first medium, and glass is the second medium, and the glass is the second medium. So I am drawing the normal. So when this ray of light traveling from air and enters the glass, the path of this light first bends. That means a refraction happens. Again, when this ray of light enters air from glass, once again refraction happens and the path of the light bends. This phenomenon is known as refraction. This phenomenon is known as refraction. The ray of light which incidents on the interface of the medium, the ray of light which incidents on the interface of the medium is the incident ray, and the ray which refracts or the ray which bends is the refracted ray, and the perpendicular drawn is the normal. The angle between the incident ray and the normal is the angle of incidence represented by small letter I, and the angle between the refracted ray and the normal is the angle of refraction and is represented by small letter r. So simply, what is the refraction? The phenomenon of bending of light when it travels from one medium to another. When it travels from one medium to another, that's simply known as refraction. That's simply known as refraction. So we have two laws of refraction. We have two laws of refraction. The first law is the incident ray, refracted ray, and the normal at the point of incidence lies on the same plane. The incident ray, the refracted ray, and the normal at the interface of two media at the point of incidence lies on the same plane. Incident ray, refracted ray, and the normal at the point of incidence lies on the same plane. This is the first law. And the second law is the important one and is known as Snell's law. Second one is the important one and is known as the Snell's law. Snell's law states that the ratio of sine of angle of incidence to sine of angle of refraction is a constant. That means sine I by sine R is a constant. Sine I by sine R is a constant. This is Snell's law. Snell's law states that the ratio of sine of angle of incidence to sine of angle of refraction is a constant, that we can write sin I by sin R, where I is the angle of incidence and R is the angle of refraction. So we can write sin I by sin R is equal to a constant, and that constant is called the refractive index of the medium, and that constant is called refractive index of the medium and is represented by small letter n. So we can write sin I by sin R is equal to small letter n, where n is known as refractive index of the medium, where n is known as refractive index of the medium. These are the two laws of refraction. Which are the laws? The incident ray, refracted ray, and the normal at the point of incidence lie on the same plane. Second law is known as Snell's law. What is Snell's law? The ratio of sine of angle of incidence to sine of angle of refraction is a constant. So we can write sin I by sin R is equal to a constant, and that constant is known as refractive index of the medium, and that constant is known as refractive index of the medium, represented by small letter n. So we can write sin I by sin R is equal to small letter n. This is what called Snell's law. Now, when we are considering two mediums, the medium having higher refractive index is known as denser medium. The medium having higher refractive index is known as denser medium, and the medium having lower refractive index is known as rarer medium, and the medium having lower refractive index is known as rarer medium. So when we are considering air and glass, the refractive index of air is approximately equal to 1 and the refractive index of glass is approximately equal to 1.6. So we can say that here glass is the denser medium and air is the rarer medium. So when light travels through air and enters the glass, that means ray of light is traveling from a rarer medium to denser medium. If it doesn't make any change, then the ray must go like this. But what happens? It bends nearer to the normal. That means it bends towards the normal. So as a general condition, we can say that when a ray of light travels from a rarer medium to denser medium, when a ray of light travels from a rarer medium to a denser medium, then it bends towards normal. Then it bends towards normal. Like the same way, the ray of light travels through the glass and enters the air. If any change doesn't make any change, then the ray must go like this. But what happens? It bends away from normal. It bends away from normal. So we can say that when a ray of light travels from a denser medium to rarer medium, it bends away from normal. It bends away from normal. So remember these two general conditions. When a ray of light travels from a rarer medium to denser medium, it bends towards normal. And when the ray of light travels from a denser medium to a rarer medium, it bends away from normal. It bends away from normal. Okay, clear? So, the laws are, first one, incident ray, refracted ray, and the normal at the point of incidence lies on the same plane. And the second is Snell's law, that is sin I by sin R is equal to a constant, and that constant is refractive index. Now we are going to discuss about the refractive index. When I am writing like this N21, this means that refractive index of medium 2 with respect to medium 1. This means that refractive index of medium 2 with respect to medium 1. This can be defined as the ratio of velocity of light in medium 1 to velocity of light in medium 2. This can be written as N21. That means refractive index of medium 2 with respect to medium 1. That is N21 is equal to velocity of light in medium 1 by velocity of light in medium 2. So it can be defined as refractive index of medium 2 with respect to medium 1 is defined as the ratio of velocity of light in medium 1 to velocity of light in medium 2. Now I am writing N12. N12 means refractive index of medium 1 with respect to medium 2. N12 means refractive index of medium 1 with respect to medium 2. This can be written as velocity of light in medium 2 by velocity of light in medium 1. This can be written as velocity of light in medium 2 by velocity of light in medium 1. So N12, refractive index of medium 1 with respect to medium 2 is defined as the ratio of velocity of light in medium 2 to velocity of light in medium 1. That is N12 is equal to V2 by V1. N12 is equal to V2 by V1. That is N21 and N12. If the first medium is air, then what happens? If the first medium is air, then the velocity of the second medium is taken as comparison with velocity of light in vacuum. If the first medium is air, then the velocity of second medium is taken as compared to the velocity of light in vacuum. Then we can write N is equal to C by V. Then the refractive index is known as absolute refractive index. If the first medium is air, then the refractive index is known as absolute refractive index. If the first medium is air, then the refractive index is known as absolute refractive index. That is N is equal to C by V, where C is the velocity of light in vacuum having value 3 into 10 raised to 8 meter per second. N is equal to C by V, where C is the velocity of light in vacuum having the value 3 into 10 raised to 8 meter per second. So N is equal to C by V, where N is the absolute refractive index. Okay, clear? The next topic we are going to discuss is refraction through spherical lens. So we need to study about two types of lens, convex lens and concave lens. Convex lens and concave lens. For a lens, we know that both the surfaces are refracting surfaces. So if the refracting surfaces curved outwards, then it is a convex lens. And if the refracting surfaces curved inwards, then it is a concave lens. If the refracting surfaces curved outward, then it is a convex lens. And if the refracting surfaces curved inwards, then it is a concave lens. So as in the case of mirror, we need to study the terms related to the lens and the center of the lens, the refracting surface, and the center is the optic center, and the axis passing through this optic center is the principal axis, and we are having focus, and we are marking it as f1 and 2f1, f2 and 2f2. Like the same case for concave lens also. So for these two lenses, convex lens and concave lens, one more thing to be remember is that convex lens converges all the light rays passing through it. Convex lens converges all the rays passing through it. So convex lens is simply known as converging lens. On the other hand, concave lens diverges all the rays passing through it. So concave lens is simply known as diverging lens. Now we need to study the image formation of these two types of lens. image formation of these two types of lens. Image formation of these two types of lens. So for studying image formation, first we need to study three basic rules. First we need to study three basic rules. First rule is that the ray of light coming parallel to the principal axis after refraction passes through the focus. The ray of light coming parallel to the principal axis after refraction passes through the focus. So we can draw, in case of a convex lens, optic center f1 to f1, f2 to f2. So the ray of light coming parallel to the principal axis after refraction passes through the focus. This is the case of a convex lens. Now we can consider the case of a concave lens. Optic center f1 to f1, f2 to f2. You all know that concave lens is diverging lens. So it diverges the ray of light passing through it. When we exchange this diverging ray, it passes through the focus. So first rule is that when a ray of light coming parallel to the principal axis after refraction passes through the focus. After refraction passes through the focus. Now the second case is that when a ray of light coming through focus, when a ray of light coming through focus after refraction passes parallel to the principal axis. So when a ray of light coming through focus after refraction passes parallel to the principal axis. Now we can look. This is a convex lens. Optic center f1 to f1, f2 to f2. So a ray of light coming through focus, after refraction passes parallel to the principal axis. After refraction passes parallel to the principal axis. In case of a concave lens, optic center f1 to f1, f2 to f2. So in case of a concave lens, the ray of light coming through focus after refraction passes parallel to the principal axis. So a ray of light, no, not in this side, it will pass through the other side because it is refraction. Now this image can be drawn once more. I will draw clearly. So in case of a concave mirror, the general condition we know that the ray of light coming through focus after refraction passes parallel to the principal axis. So this is the ray of light. After refraction, it passes parallel to the principal axis. After refraction, it passes parallel to the principal axis. And the third case is that, when a ray of light passing through the optic center, will pass through the optic center undeviated. There is no deviation. Will pass through the optic center without any deviation. Same case for concave too. Optic center, ray of light passing through optic center, passes through it without any deviation, that is undeviated. So what are the three cases? What are the three rules? First one, when a ray of light coming parallel to the principal axis after refraction passes through the focus. Second case, when a ray of light coming through focus after refraction passes parallel to the principal axis. Third case, when a ray of light coming through optic center after refraction goes without any deviation. That means it passes through the optic center undeviated. These are the three rules. Using these three rules, we need to study. Using these three rules, we need to study the image formation. Using these three rules, we need to study the image formation. So first is image formation by convex lens. First is image formation by convex lens. Image formation by convex lens. First case, we are having 6 cases for convex lens and 2 cases for concave lens. So first case, object at infinity. We need to find where the image is formed, and also we need to find the size of image and nature of image. So we can draw. This is the case of a convex lens. So I am drawing a convex lens. This is our convex lens. Principal axis, optic center, F1 to F1, F2 to F2. So where is the object? Object is at infinity, so we cannot draw the object. Only the rays coming parallel to the principal axis can be drawn. Only the rays coming parallel to the principal axis can be drawn. So we know that if the rays are coming parallel to the principal axis, then after refraction, it passes through the focus. It passes through the focus. So where is the image formed? Image formed at the focus. So we can say that image at the focus. Now look at the size of the image. The size of the image is highly diminished. Size of the image is highly diminished. Size of the image is highly diminished, and the nature of the image is real and inverted, and the nature of the image is real and inverted. So the first case is object at infinity, then the image is formed at focus, size of the image is highly diminished, and the nature of the image is real and inverted. This is the first case. Now we can move to the next case, second one. When this is interchanged, we got the second case. When this case is interchanged, second one, object at F1. I am placing the object at F1. I am placing the object at F1. We need to find whether the image is. We need to find where the image is formed. So in the second case, where is the object? Object is at F1. In the second case, object is at F1. So I am placing the object here. Here is our object. This is our object. First, a ray of light coming parallel to the principal axis. After refraction passes through the focus. Next one, ray of light passing through the optic center. passes without any undeviation. Now look, these rays are parallel to each other, not meeting here. We assume that it will meet at infinity. So we can say that image is formed at infinity. Image is formed at infinity. And the size of the image is highly enlarged. And the size of the image is highly enlarged. Size of the image is highly enlarged. And the nature is real and inverted. And the nature of the image is real and inverted. So what is the second case? Just reverse the first case, that is object at focus and image at infinity. When I place the object at f1, image at infinity, then size of the image highly enlarged, nature of the image real and inverted. This is the second case. Now we can move through the third case. Now we can move through the third case. Okay. I'm using the same image. In the third case, I am placing the object beyond 2f1. I am placing the object beyond 2f1. We need to find where the image is formed. So I am placing the object beyond 2f1. Here is the object 2f1 and one ray of light coming parallel to the principal axis after refraction passes through the focus. Next one, a ray of light passing through optic center passes through the optic center without any deviation. So where these rays meet together, these two rays meet together between f2 and 2f2. These two rays meet together at f2 and 2f2. So we can say that image between f2 and 2f2. Image between f2 and 2f2. Look at the size of the image and size of the object. We can say that the size of the image is diminished or small image. Size of the image is diminished or small image. And the nature of the image is real and inverted. The nature of the image is real and inverted. Nature of the image is real and inverted. So this is the third case. Where is the object placed? Object is placed beyond 2f1 and the image between f2 and 2f2. Image between f2 and 2f2. Size of the image is diminished and the nature is real and inverted. This is the third case. Now we can move to the fourth case. Just reverse the third case, then we get the fourth case. Just reverse the third case, then we get the fourth case. So I am placing the object between f1 and 2f1. Object between f1 and 2f1. We need to find where the image is formed. This is our convex lens. This is the principal axis, optic center, f1 to f1, f2 to f2. Where is the position of object? It is between f1 and 2f1. Between f1 and 2f1, this is our object. A ray of light coming parallel to the principal axis after refraction passes through the focus. Next one, ray of light passing through optic center will pass through the optic center without any deviation. So where these two rays meet? These two rays meet beyond 2f2. These two rays meet beyond 2f2. So we can say that image is formed beyond 2f2. Image is formed beyond 2f2. Then what is the size of the image? From the figure it is clear that the image is enlarged. Size of the image is enlarged. We got an enlarged image. Then what is the nature of the image? Nature of the image is real and inverted. Nature of the image is real and inverted. Okay. So this is the third case. Object between F1 and F2. Sorry, this is the, I think this is the fourth case. This is the fourth case. Object between F1 and 2F1. Object between F1 and 2F1. Now then we got image beyond 2F2. That is, size of the image is enlarged and the nature is real and inverted. Moving to the fifth case. Moving to the fifth case. I am placing the object at 2F1. I am placing the object at 2F1. I am placing the object at 2F1. Object at 2F1. Here I am placing the object. This is our object. A ray of light coming parallel to the principal axis after refraction passes through the focus. Okay. Next one, ray of light passing through optic center passes through it without any deviation. Without any deviation. So where these two rays meet? These two rays meet at 2F2. These two rays meet at 2F2. So the image is formed at 2F2. So the image is formed at 2F2. Now look at the size of the image. It is exactly the same size as the object. It is exactly the same size as the object. So we can say that size is same size. Size is same size. We got the same size as that of object. Now what is the nature? Nature of the object is real and inverted. Nature of the object is real and inverted. Nature of the object is real and inverted. So this is the fifth case. This is the fifth case. Object at 2F1. Where is the image formed? Image is formed at 2F2. And the size of the image, same size. And the nature is real and inverted. So moving to the last case of convex lens. Moving to the last case of convex lens. Last case, that is the sixth case. Sixth case. Object between F1 and O. Where is the object placed? Object between F1 and O. We need to find where the image is, size of the image, nature of the image. So this is our lens, principal axis, optic center, F1 to F1, F2 to F2. So the object is placed between F1 and O. Object is placed between F1 and O. This is our object. Ray of light coming parallel to the principal axis after refraction passes through the focus. Then a ray of light passing through optic center passes through it without any deviation. When this is extended to the back side, when this is extended to the back side, it will meet here. When this is extended to the back side, it will meet here. So this is the image. So this is the image. So where is the image formed? Image formed at the same side of the mirror. Image formed at the same side of the, not mirror, it is lens, image formed at the same side. So now look at the size. Size is enlarged. We got an enlarged image. Then nature, if the image is formed at the same side of the lens, if the image is formed at the same side of the lens, then the nature is virtual and erect. Then the nature is virtual and erect. If the image is formed at the same side of the lens, then the nature of the image is virtual and erect. Then the nature of the image is virtual and erect. This is the last case of image formation by convex lens. Now we need to study the image formation by concave lens. Now we need to study the image formation by concave lens. We are having only two cases for concave lens. Image formation by concave lens, we are having only two cases. So the first case is object at infinity. We need to find where the image is. Also, we need to find the size of the image and nature of the image. So now we can draw a concave lens. This is our concave lens, and principal axis optic center F1 to F1, F2 to F2. So the object is at infinity, so we cannot draw the object. Only we can draw the rays coming parallel to the principal axis. These are the rays coming parallel to the principal axis. As we all know, concave lens is a diverging lens. It diverges the ray of light passing through it. When it is extended to the back side, it will meet at focus. So we can say that image is formed at focus. Image is formed at focus. But remember, it is the same side of the lens. It is at the same side of the object. Object and image are at the same side. So the size is highly diminished or point sized. The size is highly diminished or point sized. The size is highly diminished or point size. And the nature is, whenever the image is formed at the same side, then the nature is virtual and erect. Then the nature is virtual and erect. This is the first case of concave lens, object at infinity, then the image at focus on the same side of the lens. Size of the image is highly diminished and the nature is virtual and erect. Moving to the second case, which is the last case, only two cases for concave lens. Second case, object between infinity and optic center. Anywhere between infinity and optic center, object is placed anywhere between infinity and optic center. Object is placed anywhere between infinity and optic center. We need to find where the image is formed and the nature of the image. Okay, I'm placing the object here. I'm placing the object here. This is our object. One ray of light coming parallel to principal axis. Then you know it diverges and it is extended. It will pass through the focus. Now another ray, it is passing through optic center. It passes through the optic center without any deviation. So these two rays meet here. So this is our image. This is our image. So where is the image formed? Image is formed between F1 and O. Image is formed between F1 and O at the same side of the lens. Size is diminished. It is small image. Size is diminished. It is small image. And the nature, if the image is formed on the same side, then the nature is virtual and erect. Then the nature is virtual and erect. So this is the last case of concave lens image formation, object between infinity and optic center. Where is the image between f1 and O in the same side of the lens, and the size of the image is diminished, small image, and the nature is virtual and direct. That's all about the image formation by the lens. That's all about the image formation by the lens. Now we need to study the lens formula. Last topics in this chapter: lens formula, magnification, then power of lens. Lens formula, magnification, and power of lens. So the next topic is lens formula. This is a simple equation, that is 1 by V minus 1 by U is equal to 1 by F. This is lens formula. 1 by V minus 1 by U is equal to 1 by F. In mirror formula, it is 1 by V plus 1 by U is equal to 1 by F. But in case of lens, it is 1 by V minus 1 by U is equal to 1 by F, where V is the distance of image from the optic center and U is the distance of object from the optic center. By sign convention, which is same as in case of mirror, we can say that distances towards the left side of the optic center is taken as negative and right side is taken as positive, and the upward direction is taken as positive and the downward direction is taken as negative. So the lens formula is 1 by V minus 1 by U is equal to 1 by F, where V is the image distance, U is the object distance, and F is the focal length. This is lens formula. Next topic is magnification. This is the magnification of lens. We already studied the magnification of mirror, represented by the same letter, small letter M. Magnification is defined as the height of image to height of object, ratio of height of image to height of object, which is the same definition as in the case of mirror. So magnification can be written as M is equal to HI by HO, where HI is the height of image and HO is the height of object. Otherwise, we can write M is equal to V by U. So magnification is defined as the ratio of height of image to height of object. Otherwise, M is equal to V by U. So M is equal to HI by HO or M is equal to V by U. This is magnification. Now the last topic in this chapter is power. Power means power of a lens. In the chapter electricity, you studied the electric power. Here it is power of a lens. Power of a lens is defined as the reciprocal of its focal length in meter. Power of a lens is defined as the reciprocal of its focal length in meter. So we can say that P is equal to 1 by F in meter. Otherwise, we can say that P is equal to 100 by F in centimeter. If it is in centimeter, then we can write P is equal to 100 by F in centimeter. So basically, power is defined as the reciprocal of focal length in meter. So we can write P is equal to 1 by F in meter. If focal length is given as in centimeter, then we can find the power by P is equal to 100 by F in centimeter. Same case, 100 by F in centimeter. If it is in meter, then it is 1 by F. If it is in centimeter, then it is 100 by F. And the unit of power is diopter. Represented by capital letter D. That's all about power. So now we complete the second section, refraction 2. That is all in this chapter, light reflection and refraction. So major two topics are here, reflection and refraction. In reflection, we studied what do you mean by reflection. laws of reflection, spherical mirrors, convex mirror and concave mirror, and then the image formation by convex mirror and concave mirror, then uses of convex and concave mirrors, sign convention, mirror formula, magnification. Next, in the section refraction, we studied what is refraction, laws of refraction, then refractive index, absolute refractive index, then spherical lenses, concave lens and convex lens, converging lens and diverging lens. Converging is convex and diverging is concave. Then image formation by convex lens and concave lens. Then lens formula, magnification and power of a lens. That's all in this chapter. Study well and you can score almost all the questions in this chapter when you study all these topics. Only the remaining things is the problem that we can discuss in another section. So now the chapter is over, completed. I am Nitishas signing off. We can meet with another section in another day.